In this video, we're going to derive the function for the total potential energy stored in a more general bar element, where I am no longer assuming that the cross-sectional area of my bar element is a constant, but rather it is a function of x. Likewise, Young's modulus is no longer constant, but is a function of x. And for the first time, I'm now assuming that forces are not just applied at the nodes. Here I have force P applied at node 2. Node 1 is attached to the wall. But I'm also allowing for some distributed body force being applied along the length of the bar element. The bar element, of course, has length L. Now, in the past, in order to get or derive the total strain energy inside of my bar elements, I've directly applied Hooke's law. Unfortunately, I can't do that on my more general case bar element because I can no longer assume that the stiffness is constant along the length of the bar. Hooke's law does not directly apply. However, if I look at a small differential volume inside my bar element, I can assume that the stiffness inside this very small differential volume is more or less constant. And in this small differential volume, which I've blown up here, I can apply Hooke's law. So let's see if we can first find the total strain energy stored inside this differential volume and see if that'll help us find a function for the total potential energy stored in the entire bar. So I want to find the strain energy inside this volume. Energy is work. Work is force times distance. The force I'm talking about is the force being applied to this face. And the force being applied to this face is going to equal the stress along this face in the x direction plus times the area of this face, which is dy dz. Now, work is force times distance. I need to find my distance. My distance is going to be the change in strain from this point here to this point here times the length from here to here. That's dx. So my distance is dx d strain in the x direction. So my total strain energy inside this differential volume, du, big U, is force times distance. That's my stress, dy dz, times my distance, dx d strain. You'll note that these values together here are simply dv. So if I want to now find du, is simply du is equal to my stress times dv times d strain. Now, if I want to find the total strain energy inside my entire bar element, I simply need to integrate this over the entire volume. And of course, I have to also integrate from the strain from here to here. So if I do that, I will get my total strain energy in the entire bar element is the triple integral over the volume times the integral from 0 to the strain at this value of x along this face. My stress, d strain, and of course this is the dummy variable strain because I'm integrating over that. This is the strain at this face. dV. Okay? And now I'm ready to apply Hooke's law, because you'll remember that Hooke's law tells me that my stress dx is equal to E my strain. So if I do that, I'll get that my total strain energy inside my entire bar is the triple integral over volume going from 0 to strain in the x direction. Now I have E, I'm substituting out this stress for E strain. It's inside the integral. I'm using a dummy variable, dE in the x direction over dV. Now I can integrate this. This is just going to be 1/2 strain squared after I take this integral. And since my Young's modulus is only changing in the x direction, I can take this out. I can make this, I can multiply by area, and now this integral is only in terms of x. So my total strain energy is now the integral from 0 to L. I'm going to move the 1/2 from this integration out. I'm going to get A, E. I can't move them out because both A and E are dependent on x. Strain in the x direction squared dx. Now I need to remember that I've defined previously that the definition of strain in the x direction is just du. This is u, my displacement, over dx. So this is just u, the total strain energy in my bar, so this is big U, is just 1/2 from 0 to L, A, E, du, dx squared dx. All right, so now I found a formula for the total strain energy in my system. The work done by the external forces, or that needs to be subtracted off, is a little bit easier to calculate. So I'll just go ahead and do that, and I will find that this is equal to the integral from 0 to L of my displacement times this body force, or distributed body force, x dx, plus the displacement of u2 times the force P. So u2 P, and therefore the function of my total potential energy as a function of u of x is equal to 1/2 the integral from 0 to L A E du dx squared dx minus the integral from 0 to L u FB dx minus u2 times the force applied at node 2. Okay, so now I have this function, which is a function of total potential energy stored in the system as a function of the displacements of x, as this integral minus the displacement at node 2 times the force applied at node 2. Right. In the next video, we will find an approximation to this value, which will allow us to apply the principle of minimum potential energy and to find a solution to this general case of a bar element.